Okay, so good evening, everyone. As Laura said, I will tell you something about our machine learning models in Rankacy platform, data pipelines, and how the AWS is connected to that. We will start with a bit of a context of the company and myself. At Rankacy, we have the main product as Rankacy.com, which is a platform for Counter-Strike players. Counter-Strike players are kind of data focused, and this is also the reason why we are pretty data heavy. But I will get to that. My role in the Rankacy is lead machine learning engineer. Basically, anything AI in the company goes by me. I'm not a newcomer in the field because I started my career as a researcher at university, got my PhD, and then went for the industry. But partially, I still do some research at university as well. And as I said, the Rankacy is a platform for Counter-Strike 2 players, and we provide the players with various stats that they can check for their performance. But we are not limited to that. Yeah, the platform also enables the players to generate highlights from interesting moment in the game and share it with their friends, or even use our analytical tools, like, for example, 2D map replay of the match, which they can use to check the match that they played in detail and see what went wrong. And as I said earlier, we are kind of data heavy because we are near 1 petabyte of data, because we have analyzed more than 2.5 million of CS2 matches. Currently, we have around like 50,000 of players here, so the platform is quite big. Fun fact is that we haven't started on AWS initially because the platform started as a normal web application with VPS hosting, but then the users started to grow by thousands, and we saw that it's impossible to have global platform like this built on VPS. So we have moved into the cloud in the beginning of 2024, and we are running on AWS till then. The cloud was kind of challenging for us because most of us had only like software engineering background or perhaps some data science and data analysis background, but we are no expert. We are no expert on the cloud. And we want to also, with this slide, thank to Labyrinth Labs because they helped us with the migration to the AWS in like three months. But mainly they helped us how to design the services and how to think in the cloud, because this was something that we had no experience with. And also the cloud enables us, or AWS, to scale globally because the Counter-Strike is popular worldwide. So we are not targeting only like Central Europe, but we have players from US, Asia, and so on. We will dive a bit deeper into the tech. We use pretty much standard set of services on AWS. Most of our services is running on EKS. We are using spot instances because we want to control the cost for the platform. And beside that, we are using Aurora RDS for DB. We are using the Graviton for instances for the cost control, which is kind of nice and works very well. And also we are using pure EC2 instances for some heavy workloads like C++ compilations. And also I mentioned that we are providing highlights for the player, and the highlights need to have like CS2 game running to replay the match and generate the video. There are of course some alternatives for the servers like this, because you need to run instance with Windows, and it needs to be GPU powered. But the problem with alternative solution is that you are outside of the AWS, and it is not so seamless when you have the whole infrastructure in the cloud. Majority of our data is in S3. We have a mix of standard, deep archive, and Glacier. This is something that we still fine-tune when to move which part of the data to deep archive or Glacier. And also beside that, we are using services like Elasticache or MQ for background jobs, like downloading the demo files from Steam, some analysis of, like post hoc analysis of the matches, and also we need to lower the load on database. And recently, we have also migrated our UX from React to Next.js. And for the CDN, we are using AWS CloudFront. Yeah, we use many more AWS services, but these are like the main ones. And here you can see basically the overview of the whole architecture with very high-level view on that. And this is mainly for the platform. Yeah, and because we have so much data in terabytes or hundreds of terabytes, we have decided to focus our initiative on using this data and not with only like pure data analysis or statistics, but we started building our own machine learning models. The reason for that is that we were on various AWS summits. Mainly, we would like to point out the one in Dubai. And there were presentations by Formula 1 or Bundesliga and how the AWS is supporting the sports and the teams with analytical tools. And we saw that and said, okay, this is something that we are able to also build for the Counter-Strike players. Yeah, so it was great source of inspiration for us. And we decided to build similar tools, like, for example, models for vector embedding, which enables the players to search for similar situations based on setup or text description. Also, beside that, we are running some prediction models, which can tell you the outcome of the match or who will survive or kill someone in next, let's say, 3 seconds, yeah, and so on. But we will get to that. If somebody is interested in AI or data engineering in general, we can definitely recommend the Dubai Summit for that, because this was kind of focused on this topic, perhaps even more than summits in Europe, which some of my colleagues also went to. And now we are getting to the data and machine learning stuff finally. We have a lot of data on S3, but beside the AWS, we also have own on-premise servers for some R&D and also other projects not connected to Counter-Strike in different domains. So we have decided to build the first model on the on-premise servers, yeah, because we have multiple GPUs, we have it available 24/7. But the problem was that we had the data in the cloud, yeah? So the first challenge was how to move the data to on-prem, yeah? Because when we thought about that, we said, okay, we can download that, but the cost was like $15,000 US, so it was impossible for us, and we would need to wait a few weeks to download the data. But then we have discovered AWS Snowball, which is service that enables you to copy the data from the S3 to some box, which you can imagine as some like Synology NAS or small desktop PC. And you can have your data delivered by standard service like UPS to your on-premise location. Yeah, this is how it looks like. It's like desktop PC box with various network interfaces, Ethernet or optical ones. And one of the Snowball boxes can move, I guess, up to 80 terabytes of data. Yeah, and this is the solution that we went for. And in the end, the whole cost was like $6,000 US, and we had the data in the on-premise location like in 2 days. Yeah, so it was pretty seamless. And when we had the data, we have plugged the Snowball device into our network and just used the AWS CLI to copy the data. There is a small tip from me, because the Snowball also have option to use NFS. So we say, okay, we can use the NFS, no problem, but you need to enable the NFS service before you order the Snowball. Because if it comes disabled, you cannot turn it on afterwards. Yeah, so this is something to take care if you use the AWS and NFS. When we had the data on the server, we started to building the data lake. We are using Delta tables. If you are familiar with Databricks or Spark, this is something that you might have heard of. It's basically the Parquet-based data format with very good compression ability. And also, what is cool about Delta tables, it can use something called Z ordering or liquid clustering. And this is basically indexing of the Parquet files, which is important for fast retrieval of the data for the machine learning models. We are using standard medallion architecture, like bronze, silver, and gold level of the data. The bronze level of the data contains like just parsed time series data from the demo files from the CS2. And then we started to filter the data to the silver and also do some feature engineering in the gold level, which is directly tied to the machine learning models. And this is how the whole pipeline basically looks like. We started with the data on SS3 and moved that to on-premise servers. And then using Polar's library mainly, we have built the data engineering pipelines. You can see that we have started with like 95 terabytes of raw data and ended up with 9 terabytes of bronze data, 6 terabytes of silver. And in gold, it's actually 20 terabytes, but normally it would be even less for the silver. But the problem here was that you need to have usually specifically saved the data for the machine learning models or the deep learning models to be able to retrieve it very fast and have high utilization of GPUs. And because of that, we have many versions of the gold data. Basically, each iteration of the model has its own gold level data. Yeah. And now something about the models. Because we are having terabytes of data, it's clearly a task for neural networks. We have decided to build a model on transformer architecture, which is something that, for example, LLMs are using. Our model have like 70 millions of parameters. For reference, Google BERT have like 100 millions of parameters. Yeah? So the model is quite big. It has long-term and short-term abilities to predict things. For example, for the long-term predictions, you can predict outcome of the whole match or single round in the Counter-Strike. And for the short-term predictions, we are focusing more on player behavior stuff, which can be prediction of survival of the players or some events in the game, like if the bomb will be planted in the next 5 seconds, for example. And this is the general architecture of the model. We are using the mix of various smaller or bigger transformer blocks in the model, because in the beginning we start with general tokens, and the tokens are data about individual players, like positioning, equipment, health, armor, and stuff like that. And then we combine the tokens with 2 strategies. One is called horizontal, which is basically like freezed state of the game, like what is happening right now without any time context, like 1 frame in the game. And we learn the interactions among the players, grenades, or certain events that are happening. And beside that, we also have vertical strategy, which is more time series oriented. And with these strategies, we are feeding the model the sequences of this time step for each player. And the model learns, for example, movement patterns. When we have it, we combine that into aggregated tokens, like, for example, team tokens for terrorist and counter-terrorist team. We are also using things like masking tokens for dead players and so on. And when we have it ready, we feed these tokens to the main transformer block. We also enrich the data with other things like current map, some streams of damages, skills, thrown grenades, and so on. And then we get the basically latent vector representation, which is called CLS token usually, which is a vector which is fed into the classification heads, and the classification heads give you the final predictions for the outcome of the round, survival, and many, many more. And this is one of the example use cases of the model, because the model can give you prediction of the winning side of the round in each moment of the game, like in each second. And sometimes the probability for winning for the terrorist or counter-terrorist shifts abruptly in one moment. And this moment is called impact situation. This is similar to normal sports because, for example, in football, the analysts also use things like that, and AWS have some solutions which powers them to detect that. And we are able to detect these situations in Counter-Strike. And not only that, we are also connected LLM to the output of the model, and we are describing what happened in these situations. Yeah, so the players have the full overview, or the trainers for the esports team, why the situation is impactful. And beside that, as I said, we are also dealing with shorter term predictions, which is situation like this, that in the top right corner, you can see that there is a shootout between two players. And there is this table with probabilities of survival for the next second, 2 or 3 seconds. And in the shootout, the player with the orange circle have lower probability of survival, and in the end, after the shootout, he really dies. Yeah, so this is something called like micro interaction in the game, and the model is also focusing that. And to be able to detect the impact situation and mainly explain them, we have also built custom tools for analyzing the models, because with neural networks, a lot of people will tell you, okay, this is black box, some computation runs in the model and nobody knows what's happening. Yeah? This is only partially true, because with, for example, transformer architectures, you can analyze the model very deeply, and you can basically freeze the model and take a look what is important for the model for the current prediction at any moment. Yeah? So you can analyze the individual transformer blocks, like the encoders, or even the attention heads. And when you know it, you can check directly the vectors and the attention maps for the individual tokens. And because of that, you can find what features are important for the current prediction. And when you know it, you can connect this data with the LLMs and select only the important subset of the data and let the LLM explain the situation, yeah, instead of feeding everything about the situation at once, because this will lead only to hallucinations. Yeah, and this is example of the tool. Yeah, we use it mainly for internal debugging purposes, but this is also the key component for the connection between the model and the LLM. And when we were building the model, we faced pretty tough challenges. Mainly, it was connected to hardware with on-premise servers, yeah, because we were running multiple GPUs to train the model, And sometimes we faced instability in the training in terms of drivers or NVIDIA libraries. Yeah, for example, we had exactly the same code which crashed after 6 hours on some nickel error, and then we just rerun the code and it went for like a whole week without any error. Yeah, so pretty random stuff. Also, as I said, we are using Polars library for processing the data. The library is great because it has Python API. It's similar to Pandas, so it's easy to use. But the problem is instability of this library, because many times we have upgraded or downgraded the Polars library and ended up with completely different times for querying the data. Yeah, once we had the whole batch loaded in 7 seconds, and then with only a minor update of the library, we went to like 25 seconds. Yeah, so it was kind of unstable. And also, we are using the Delta tables, and we started without Spark, which was uncool this decision in the end. Because Polars is using Delta RS under the hood, which is Rust implementation of the Delta Tables API. But the problem here is that it's kind of unstable and incomplete. Yeah, so for some operations, like for example, managing the tables, calculating the indexes, vacuuming of the unused Parquet files, and so on, we needed to have a Spark cluster running and use it for that. Also, for example, the writers to Parquet are more optimized in the Spark compared to Delta RS or Polars. And when we had the model trained and running, we have decided to also export it to like standard formats, like Onyx or TorchScript, and another issues emerged, because we have found out that the Onyx or TorchScript is not supporting everything for the transformers and attention mechanisms. Yeah, and we have some masking of tokens and conditional paths in the models and so on, and the support for this was problematic. So even exporting of the model from PyTorch was an issue. And also with running on-premise, you face challenges like overheating of GPUs, yeah, pretty common. And also we had issues, for example, with wrong BIOS settings, because we had server by ASUS with AMD EPYC CPUs, and there are some settings in the BIOS which prevent the communication among GPUs using nickel, and you need to fall back to other options which are much slower. Yeah, so next time we'll definitely use AWS for training, because we have learned our lessons. We learn a lot with the on-premise solution, mainly in terms of optimizing, for example, the data loaders and the data pipelines, like to the core. But we think that running on the cloud has its own advantages, and perhaps the process would be much easier next time. And now our focus for the next months is deploying these data pipelines and model to AWS. We have built a solution in mind with the option to migrating to the cloud in mind, because this is something that we need to do. But we are still building this, and currently we are experimenting with AI native solutions by Amazon, like SageMaker, for example, for inference of the model, or even the managed Spark clusters with EMR or Glue, yeah, which are very helpful for us, because we don't need to manage the Spark ourselves, and we only use it for some parts of the pipelines. Majority of the code is still in Polars. Yeah, and this is basically our plan to finish that before Christmas. Okay, so that's all for me. Thank you for your attention. If you have any questions, I'm free to answer that, or you can find me here or even message me on LinkedIn. Thank you. Okay.
Have you considered Iceberg or
Yeah. Yes, we have considered that because Iceberg or Apache Hudi are direct competitors to Delta Lake. I know that currently the main focus for these Parquet-based stores is Apache Iceberg in AWS because they are natively supporting that even in S3. But when we started to building the pipelines and the data lake, we have decided to use Delta tables because it supports the indexing with the Z order or even the liquid clustering. Yeah, the liquid clustering is cool, but the problem is that it's only supported in Spark currently. And for example, with tables with liquid clustering indexing on, you cannot read it in polars, yeah, which is kind of problematic for us. Yeah, but the Iceberg is another option, and I think it's viable for this as well.
So it was a matter of more functionality.
Exactly, yeah. Of course.
What is the whole use case of this? You somehow monetize the outcomes of these matches, or you're just using as data for something else, or what?
Currently, it's meant for players or trainers for the esports team for analysis, because normally when you have the CS2 match, it's like half an hour of gameplay. And if you want to find the impact moments, for example, you need to watch the match and mark them. Yeah, this is impactful, this is not. And the model enables you to detect this automatically. Yeah? And the next step for us is also feeding in the live data to have it available, for example, for betting.
But someone plays for the outcomes of the Counter-Strike matches, or?
People bet on this. Yeah. Okay.
Did I get it right that for make inference on data, you kind of label or tag somehow with your file, right? Like this data from Counter-Strike, and like you don't get the data for this big file. You kind of work with the whole file and tag it somehow, or you have data for it,
Okay, I'm not sure if you are asking about processing the raw files from Counter-Strike.
No, you show us that
Okay.
when you start make inference in SageMaker.
Mm-hmm.
So it's live or it's batch?
Currently, it's batch because we are using these tools for post-analyzing of the game, and the real-time inference is something that we plan to have in Q1 next year. But I think that it comes with different challenges because, for instance, currently we are able to infer the whole match of the Counter-Strike in a few seconds. But it's in the batch mode. If you have it live, you have like batch size of 1, and this is kind of different game.
Understand.
Mm-hmm.
I am asking about like, okay, taking the data, what is the input for the model?
Basically, the Counter-Strike demo files can be parsed into parallel time series data, and example of such data is, for example, the position of each of the 10 players, or the equipment, which buttons they are pressing, if there is some smoke grenade active in the map, or even you can have some aggregated features, like, for example, what is the total equipment value for the whole team, or how many sniper rifles do they have, and so on. Yeah, this is mainly about data engineering, but this is a bit domain specific. But these are the inputs for the model. And for the model that I've presented with like 70 million parameters, the model is sequence-based. So you cut this time series data into like small subsets of 96 subsequent frames from the game, and you feed these subsets of the data to the model. Mm-hmm. That's okay, perfect. Okay.
You mentioned it somewhat, but I don't remember how much it cost you to transfer data on-prem. It was 60 terabytes of?
Yes, it was like 68 of compressed data because the raw DEM files can be compressed with that standard library very efficiently. And the original cost for downloading was like 15,000 of US dollars, but this is only estimate. We haven't tried that. But for the Snowball, it was 6,000 of US dollars.
6,000. And do you transfer those data repeatedly or?
No, it was just one time to build the first prototype of the model, and the plan is to deploy the model and continue with fine-tuning the model on AWS.
So how much time do you have to actually download the data? Because you don't buy the server, right? You just rent it, the data.
We own the server.
I mean, the Snowball from
The Snowball, oh, okay. It is for 10 days. And after that, you can extend the period, and you pay basically day by day. Yeah.
How much does it cost per day, for example?
We managed to move the 68 terabytes in like 7 days.
Oh, okay. So
Yeah, it's quite fast. Yeah.
I'm not expert in AI, but what kind of model is this GT or GRTB?
The GPRT. Okay.
How is different? What's the difference if I see standard LLM GPT
Mhm.
model, like they have this prefill and they code
And encode. Yeah. You get it right. The difference in here is with the tokenization, because with GPT models, you tokenize text. For simplicity, you can tokenize text with single words or n-grams. Yeah, this is simple. But if you are building something proprietary, like for instance this Counter-Strike focused model, you are not able to use text-based model, yeah, because the game is dynamic, it's mix of aggregated features and movement of the players and stuff like that, and you need to find out how to tokenize this data to fit in with the transformer model, yeah? And this is the main challenge, and this is also the reason why we have these tokens for players with all the info like focused on individual players, and then in the model we build the hierarchy of the tokens, like the team tokens and so on, and this is the difference with the LLMs. Yeah, we share the same technology, like attention mechanisms, transformer blocks, yeah, and all the cool stuff, but the processing of the data is custom built for this task. So it's kind of like mix of specific AI models and foundation one, because we are able to feed basically the whole game state into model and have multiple predictions for multiple tasks, which is like in GPT, because you can translate text, have summarization, generate, and stuff like that. And we are using the same strategy, but our model works only for CS2 currently. Thank you.
Which kind of storage do you use on-prem? Do you use some local NAS or do you use some distributed storage like Ceph or Mini.io?
We have XFS, but we have only one server, yeah, with multiple GPUs. So we have RAID for SSD drives and hard drives, and this is basically it. Yeah. Currently, we have only like software RAID, yeah, for this.
Are you afraid of losing the data since you have it in one location? Only in RAID setup?
It can be an issue. We have the server in data center, so we are not afraid of things like floods or something. Yeah, but the server is meant only for R&D purposes. So even if we lose the data, it's not so problematic because we have everything in the S3 still. Yeah. So and now we would be able to build the whole model in S3 in AWS as well. Yeah. So not a big deal.
Does the updates, does the updates impact the model? Like updates of the game, does that impact the model?
Yeah, it has impact because the updates in the game, for example, change the economy, and it brings a different mix of like buy-ins in the equipment. So this is something that is problematic, and we are fine-tuning the model for that. Yeah, so if there is some update, we wait for a bit for the new data, and then we don't run the whole training loop again, which takes like multiple days to train, but we only use the new data, mix it with some old instances to have some balance, and then fine-tune the model, which may took like few hours only.
So basically, let's say
Mm-hmm.
some rifle costs more or
Mhm.
do more damage. So basically, all the data you got about this rifle
Mhm.
throw to the trash, or
It's not like put into the trash because still the game dynamics are the same. Yeah, the projectiles have certain speed, you have certain ammo value, and so on. There is just the change for the single weapon. Yeah, so the fine tuning can solve that. But of course, these distribution shifts in the data are problematic in general in machine learning. Yeah, so this is a good point.
question?
So what does the I in GPIT stand for?
The GPRT is like general pre-trained Rankacy transformer.
I see, okay. It's
Okay.
group idea.
Did you also try to like look for other games where you could use this?
Yeah, we have, because currently we are looking into simulation softwares, like for example VBS4, which is kind of like a game because it's similar, for example, to Arma, if you know the game, and this is one of the another possible use cases to basically take all the know-how that we have from building the data pipelines, modeling that, and feature engineering, and build similar model but for different game or domain. Okay, so anything else? Okay, if not, we can continue with the discussions after that. Thank you very much.